There's a moment in the life of every star where it reaches the end of its journey, a final, cataclysmic explosion so bright it outshines entire galaxies. We call it a supernova, and it's supposed to be the grand finale, the last act in a star's existence. But what if I told you there's a supernova out there that refuses to follow the rules? A cosmic rebel that's been exploding for decades, defying everything we thought we knew about how stars die. This isn't just a fleeting flash in the dark, it's an unfinished masterpiece, a stellar explosion that's still writing its own final chapter. And today, we're diving deep into the heart of this celestial mystery. Picture this, a star millions of times brighter than our sun, erupts in a blast so violent it sends shockwaves racing through space. Normally, that would be the end of the story. The light fades, the debris scatters, and all that's left is a faint remnant. But this supernova, it's different. It's been glowing, pulsing, even brightening again long after it should have vanished. Astronomers are baffled. What could possibly fuel such a prolonged explosion? Is there some hidden force at work, some cosmic secret we've yet to uncover? The answers might rewrite the textbooks on how stars live and die. This isn't just a curiosity, it's a window into the universe's most dramatic and enigmatic processes. Every flicker of light from this unfinished supernova holds clues about the forces that shape our cosmos, from the birth of black holes to the creation of elements that make up everything around us. And here's the thing, you don't need a telescope to feel the wonder of this discovery. It's a reminder that the universe is still full of surprises, that even the most well-understood laws of physics can be upended by something as simple and as extraordinary as a star that refuses to go quietly. So let's unravel this mystery together, piece by piece, and see what secrets this cosmic anomaly is waiting to reveal. Most supernovae follow a familiar script, a brilliant flash, a dramatic peak, and then a slow fade into cosmic history. But the one we're talking about, it's like a star that just won't take its final bow. When astronomers first spotted it in 2014, they expected it to dim within months, like every other supernova before it. Instead, it kept shining, even brightening at times, as if some unseen hand was stoking the flames of its destruction. This isn't just a delayed finale, it's a complete rewrite of the rules. So what's really going on here? For starters, most supernovae mark the violent death of a massive star, collapsing under its own weight before rebounding in a single, catastrophic explosion. But this one behaves more like a car with a stuck gas pedal. It keeps erupting over and over, as if the star's core is somehow feeding the fire long after it should have burned out. Some theories suggest it might be a rare type of supernova fueled by an unstable core, or perhaps even a star so massive its death throes play out in slow motion. Others wonder if it's interacting with hidden companions or dense clouds of debris, prolonging the explosion in ways we've never seen. The strangest part. This isn't just a scientific oddity, it's a cosmic laboratory. Every flicker and flare holds clues about the extreme physics at work when stars die. Normally, supernovas seed the universe with heavy elements, from the iron in our blood to the calcium in our bones. But this prolonged explosion could be forging elements in ways we don't yet understand, or even hinting at new pathways to black hole formation. Every extra day it lingers gives astronomers more data to crack the code, turning what should have been a fleeting moment into a years-long masterclass in stellar demise. And that's the real magic of this unfinished supernova. It's not just breaking the rules, it's teaching us how little we truly know. The universe loves a good plot twist, and this one's keeping us on the edge of our seats. Will it fade tomorrow, or could it keep defying expectations for years to come? One thing's certain: as long as it keeps shining, we'll be watching. When astronomers first trained their telescopes on iPTF14hls in 2014, everything about it seemed ordinary at first. Like countless supernovae before it, this one flared brightly in the night sky, a predictable beacon signaling a star's final moments. But then something extraordinary happened. Instead of fading away over weeks or months as expected, this cosmic anomaly did the unthinkable. It grew brighter again, and then again and again. For nearly 3 years, this stellar rebel pulsed with energy, defying every textbook description of how supernova should behave. What makes this discovery so revolutionary isn't just its defiance of expectations, it's the sheer scale of that defiance. Imagine watching a firework explode in slow motion, its sparks reigniting mid-air over and over. That's essentially what astronomers witnessed, except instead of gunpowder and paper, this was a star with 500 times the mass of our Sun refusing to die quietly. The data was so bizarre that scientists initially questioned their instruments, running check after check to rule out errors. But the truth was undeniable: they'd found something that shouldn't exist. The implications sent shockwaves through the astrophysics community. For decades, supernova had been considered one of the universe's most predictable cataclysms, a straightforward process where a star collapses, rebounds, and explodes in a single, spectacular event. iPTF14hls shattered that simplicity. Its erratic behavior suggested entirely new physics at play, possibly involving a never-before-seen type of pulsational supernova where the star experiences multiple explosions before its final collapse. Some researchers even proposed it might be evidence of a theoretical pair-instability supernova, where a star so massive becomes its own antimatter factory, triggering staggered explosions as its core battles between collapse and revival. But here's where the mystery deepens. When scientists looked back at archival images of the same patch of sky, they found evidence of another explosion in the exact same location in 1954. That's right, this star may have survived a previous supernova event 60 years earlier, something thought to be physically impossible. It's as if the universe handed scientists a riddle wrapped in a paradox, a star that can apparently cheat death multiple times before its true finale. This revelation didn't just challenge existing models, it demanded entirely new ways of thinking about stellar life cycles. The more we learn about this cosmic rebel, the clearer it becomes that the universe still holds surprises that can upend centuries of astronomical understanding. The concept of a star dying in slow motion might sound like science fiction, but this bizarre supernova is making scientists reconsider everything they thought they knew about stellar death. Normally, when a massive star runs out of fuel, its core collapses in a fraction of a second, triggering a shockwave so powerful it rips the star apart in one blinding flash. That's the standard script: quick, violent, and final. Yet this cosmic rebel flips that script entirely, flickering like a candle in the wind, its explosions staggered over years instead of moments. So what could possibly explain such behavior? One leading theory points to something called a pulsational pair-instability supernova, a phenomenon so extreme it sounds like something from a physicist's wildest imagination. Here's how it might work. In stars with masses between 130 and 250 times that of our Sun, the core can become so hot that it starts producing matter and antimatter pairs particles and their mirror opposites. This process saps energy from the star's core, making it unstable. Instead of collapsing all at once, the star experiences a series of violent eruptions, each one blasting away layers of the star while leaving the core intact, at least for a while. It's like a cosmic version of peeling an onion. with each explosion stripping away another layer until the star finally exhausts itself and collapses for good. But even this theory has its limits. If iPTF14hls were a textbook example of a pulsational pair-instability supernova, it should have faded much faster. Instead, it kept shining, even flaring up multiple times, almost as if it was drawing energy from some hidden source. Could there be another layer to this mystery? Some researchers speculate that the star might have been surrounded by dense shells of gas ejected during earlier eruptions. As the final explosion's shock waves plowed into these shells, they could have lit up again, creating the illusion of repeated outbursts. Or perhaps the star had a hidden companion, another star, or even a black hole interacting with the debris in ways we don't yet understand. The more we study this cosmic oddity, the clearer it becomes that our understanding of stellar death is still full of gaps. Supernovae were supposed to be the universe's most predictable explosions, yet here we are, staring at one that laughs in the face of convention. Every new observation chips away at old assumptions, forcing us to rethink not just how stars die, but how they live. Because if a star can explode, fade, and then explode again, what else have we been getting wrong? This isn't just about solving a single cosmic riddle. It's about rewriting the rules of stellar evolution, one flickering explosion at a time. And with every new clue this supernova reveals, we're not just learning how stars die, we're discovering how much more there is to learn. To understand why this supernova behaves so strangely, we need to look at the extraordinary life of the star that created it. Stars 50 to 100 times more massive than our Sun don't just live differently, they rewrite the rules of stellar physics. While our Sun will burn steadily for billions of years, these hypergiants are the universe's high-speed thrill seekers, blazing through their fuel in just a few million years. But it's not just their speed that sets them apart, it's the extreme conditions inside them. At these staggering masses, a star's core becomes so dense and hot that it starts playing by quantum rules we rarely see elsewhere. The pressure is so intense that light itself struggles to escape, bouncing around for thousands of years before finally reaching the surface. These stars don't just burn hydrogen like our Sun. They layer elements like an onion, fusing heavier and heavier materials in shells around their core. Helium, carbon, neon, oxygen all stack up until the star resembles a cosmic pressure cooker, with iron accumulating at its heart. And that's where the real trouble begins. Iron is the ash of stellar furnaces. It doesn't release energy when fused, it absorbs it. So when enough iron builds up, the star's core suddenly has nothing left to push back against gravity's relentless crush. In most stars, this leads to an instant collapse and rebound, the classic supernova. But in monsters like iPTF14hls progenitor, the story might not be so simple. Some theories suggest these hypergiants experience partial collapses, like a building whose floors give way one at a time instead of all at once. Each collapse triggers a smaller explosion, ejecting layers while leaving the core intact until the final, catastrophic failure. This staggered death could explain why we're seeing such prolonged fireworks, but here's the twist: even among hypergiants, this behavior is bizarre. Most stars this size are thought to either explode completely or collapse straight into black holes without a show. That's why iPTF14hls is more than just an oddity. It's a missing link, forcing us to reconsider where the boundaries lie between different types of stellar deaths. Could there be a whole spectrum of supernova we've been overlooking, each tied to subtle differences in a star's mass, rotation, or composition? The more we study these cosmic giants, the clearer it becomes that their lives are far more complex than we imagined. They're not just bigger versions of ordinary stars, they're laboratories for physics we can't recreate on Earth. where matter behaves in ways that challenge our best models. And when they die, they don't just fade away, they leave behind clues that force us to rethink everything from element formation to the birth of black holes. In that sense, this unfinished supernova isn't just a mystery, it's a gift, offering us a front-row seat to processes we never knew existed. What's truly humbling is realizing how much we still don't know. For all our telescopes and supercomputers, the universe keeps reminding us that its most spectacular events don't always follow the scripts we've written. And that's what makes discoveries like this so thrilling. They're not just answers, but invitations to ask better questions. Normally, when a star goes supernova, the energy release follows a predictable curve, an initial brilliant flash followed by a steady decline as the explosion's shockwaves expand and cool. But this cosmic rebel breaks all the rules, maintaining its luminosity not for weeks, but for years on end. It's as if someone left the cosmic lights on and forgot to turn them off, defying every law we thought governed stellar explosions. What could possibly sustain such an extraordinary energy output? One tantalizing possibility involves a magnetar, a newborn neutron star spinning at incredible speeds, wrapped in a magnetic field trillions of times stronger than Earth. As it rotates, this stellar dynamo could be converting its rotational energy into light, effectively acting like a celestial battery, recharging the fading supernova. Imagine a firework wired to a power supply, reigniting itself long after its initial burst should have fizzled. That's the kind of sustained brilliance we're seeing here. But there's another, even more exotic explanation. What if a black hole is pulling material from the surrounding debris, creating an ongoing cosmic feeding frenzy? As gas and dust spiral inward, friction heats them to unimaginable temperatures, releasing torrents of energy that could explain the supernova's stubborn glow. It's like throwing logs on a fire, except in this case, the logs are chunks of a dead star, and the fire burns hotter than anything in our solar system. The most exciting possibility, though, is that we're witnessing physics beyond our current understanding. Supernova were supposed to be straightforward gravity winds, the star collapses, and boom. But this prolonged spectacle suggests forces at work we haven't even imagined yet. Could there be quantum processes inside collapsing stars that delay their final demise? Or interactions between matter and dark energy that somehow stretch out the explosion? Every extra day this supernova shines is another day we're forced to question what we thought we knew. What makes this mystery so compelling isn't just the scientific implications, it's the sheer audacity of nature to surprise us. After centuries of cataloging the stars, we're still discovering phenomena that rewrite the textbooks. This supernova isn't just a cosmic oddity, it's a beacon, illuminating the gaps in our knowledge and challenging us to think bigger. Whether it's powered by a hidden magnetar, a ravenous black hole, or something entirely new, one thing is certain: the universe still has secrets to share, and this stubborn explosion is just the beginning. The pulsational pair-instability theory might just be the key to unlocking this cosmic enigma. Imagine a star so massive that its core becomes unstable long before its final collapse, so hot that particles of matter and antimatter start popping into existence spontaneously. These particle pairs suck energy straight from the star's heart, weakening its internal support. Gravity gains the upper hand, triggering a partial collapse, but instead of a full explosion, the star violently ejects its outer layers in a series of eruptions, like a cosmic engine misfiring. Each outburst peels away another shell of stellar material while leaving the core intact, buying time before the final, catastrophic detonation. This staggered death could perfectly explain why iPTF14hls brightened multiple times over years. We weren't seeing one explosion, but several, each one a desperate gasp from a star fighting its own demise. The ejected material would form dense shells around the star, and when the ultimate collapse finally came, the shockwave would slam into those layers, lighting them up like fireworks in sequence. It's a spectacular cosmic domino effect where each eruption sets the stage for the next. Yet if this theory holds, why don't we see more supernova behaving this way? The answer lies in the extreme conditions required. Stars capable of pulsational pair instability are incredibly rare. They need to be born with masses between 130 and 250 times that of our Sun, a narrow window where the core is unstable enough for partial collapses but not so massive that it immediately forms a black hole. Even then, these stars must avoid losing too much mass through stellar winds during their short, turbulent lives. It's like walking a tightrope across cosmic scales. One misstep, and the star either explodes normally or collapses without a trace. Adding to the puzzle, these explosions should theoretically be brighter than what we observed. Some researchers suggest the missing energy might have been swallowed by a black hole forming at the core, or perhaps the ejected material was spread unevenly, dimming our view. Others propose that iPTF14hls wasn't a pure pulsational pair instability event at all, but something even stranger, a hybrid where the star's rotation or magnetic fields altered the process. What's clear is that this supernova isn't just challenging our understanding of stellar deaths, it's revealing gaps in our knowledge of stellar births. To produce such a massive, unstable star, the conditions in its host galaxy must have been extraordinary, hinting at environments where stars form differently than in our own Milky Way. Each flicker of light from this cosmic rebel isn't just a farewell. It's a message written in the language of extreme physics, waiting to be decoded. While the pulsational pair instability theory offers compelling explanations, the scientific community is far from settling on a single answer for this cosmic anomaly. Some researchers propose an even more dramatic scenario. What if this wasn't the death of one star, but a catastrophic collision between two? Imagine two massive stars locked in a gravitational dance, spiraling closer over millennia until they finally merge in a titanic explosion. The resulting fireball could release energy in erratic bursts, mimicking the staggered brightening we've observed. It's like throwing gasoline on a bonfire. The initial blast might fade, but the lingering fuel could ignite secondary explosions, stretching the spectacle far beyond a typical supernova. Then there's the black hole hypothesis. Picture a massive star with a dark secret, a black hole companion hidden in its orbit. As the star reaches its final days, the black hole could begin devouring it from the inside out, like a cosmic parasite. The infalling material would form a searing hot disk around the black hole, beaming intense radiation into space. This slow, violent feast might explain the supernova's prolonged glow, with each flare corresponding to another chunk of stellar material being torn apart. It's a grim but fascinating possibility. A star's death throws amplified by the very object that's killing it. But the theories don't stop there. Some scientists speculate about even more exotic explanations, like interactions with dark matter. Though invisible, dark matter's gravitational influence is everywhere. What if this star was embedded in an unusually dense cloud of it? As the star collapsed, dark matter particles might have annihilated each other in its core, releasing extra energy that prolonged the explosion. It's a long shot, but in a mystery this profound, no idea is off the table. What's remarkable isn't just the diversity of theories, it's how each one challenges our understanding of the universe in different ways. Colliding stars rewrite the rules of stellar dynamics. Black hole interactions reveal how extreme gravity can distort death itself. And dark matter, if proven, it would be our first glimpse of how this elusive substance behaves in the most violent cosmic environments. The beauty of this debate is that every unanswered question is an opportunity. With each new observation, astronomers inch closer to the truth, whether it confirms one of these wild ideas or reveals something entirely unexpected. That's the thrill of frontier science sometimes. The universe's greatest gifts are the mysteries that refuse to be solved too easily. Studying this cosmic rebel isn't just a scientific challenge. It's like trying to solve a puzzle with half the pieces missing from halfway across the universe. At nearly 500 million light-years away, iPTF14hls might as well be on the other side of a frosted window. Every flicker of light we detect today began its journey when early sharks still swam Earth's oceans, making real-time observations impossible. Add its erratic brightness swings to the mix, and you've got a recipe for astronomical frustration. This is where our most powerful eyes in the sky become indispensable. The Hubble Space Telescope, with its crystal-clear vision above Earth's distorting atmosphere, captured crucial details in visible light, revealing not one, but multiple expanding shells of debris that suggest repeated explosions. Meanwhile, the twin Keck telescopes in Hawaii turned their massive mirrors toward the supernova, splitting its light into rainbows of data that revealed chemical fingerprints no one expected. These instruments caught elements like calcium and titanium floating where they shouldn't be, hinting at layers of stellar material ejected at different times. Yet for every answer these observations provide, they spawn new questions. The supernova's light curve, its pattern of brightening and dimming, doesn't match any known model perfectly. There are gaps in the data where clouds of cosmic dust blocked our view, or when telescopes had to point elsewhere due to scheduling constraints. It's like listening to a symphony with occasional instruments dropping out. You can piece together the melody, but the full orchestration remains a mystery. The technological arms race in astronomy might soon change that. Next-generation telescopes like the Vera-C, Rubin Observatory, set to begin scanning the entire visible sky every few nights, could catch similar supernova earlier in their outburst. Space-based infrared observatories like JWST peer through dust clouds that veil crucial details, and gravitational wave detectors might one day feel the ripples from such colossal explosions, giving us an entirely new way to study stellar deaths. What makes this pursuit so thrilling isn't just filling in the blanks. It's the realization that we're witnessing a cosmic phenomenon that earlier generations of astronomers couldn't have dreamed of detecting, let alone studying in such detail. Every limitation in our current technology isn't just a barrier, it's a signpost pointing toward future discoveries. The light from this supernova traveled 500 million years to reach us. Perhaps in another decade, our tools will finally be sharp enough to decipher its full story. Most supernovae are cosmic flashbulbs, brilliant for weeks, then gone. Take SN 1987A, one of the most studied stellar explosions in history. It lit up the night sky in February 1987, peaked for about 3 months, then faded to obscurity within a year. That's textbook behavior. But iPTF14hls, it's more like a stubborn ember that refuses to die, still glowing nearly a decade after its initial eruption. The difference isn't just dramatic, it's revolutionary, forcing astronomers to rethink how we categorize these explosions. The classic supernova playbook splits these events into 2 main types. Type I involves a white dwarf stealing material from a companion until it detonates like a cosmic grenade. Type Roman II marks the collapse of a massive star's core, triggering a shock wave that blasts its outer layers into space. Both follow predictable brightness curves with minor variations. Then there's iPTF14hls, which fits neither mold. Its light curve looks like a seismograph during an earthquake, spiking, dipping, then spiking again over years. If typical supernova are fireworks, this one's a bonfire that keeps getting doused with gasoline. What's even more baffling is how it stacks up against other long-lasting stellar explosions. Some supernova, like SN 2005GL, have shown prolonged glows, but only because their shockwaves hit dense clouds of pre-existing gas, like a wave crashing into a seawall. iPTF14hls defies even that explanation. Its spectral fingerprints reveal elements like hydrogen and helium in patterns that suggest the star itself is the source of these erratic outbursts, not external material. It's not just interacting with its environment differently, it's dying differently. This anomaly throws our classification system into chaos. Astronomers now wonder if we're missing an entire category of supernova, ones where stars die in slow motion, or perhaps even revive temporarily before their final collapse. Imagine if hurricanes were suddenly spotted that lasted for years, or earthquakes that rumbled intermittently for decades. That's the scale of disruption iPTF14hls represents for stellar astrophysics. It's not just an outlier, it's a harbinger of phenomena we never thought to look for. The implications ripple outward. If this supernova isn't alone, if there are others like it hidden in archival data, or waiting to be discovered, then everything from how we measure cosmic distances to how we model galaxy evolution might need adjustment. Supernova have been cosmic yardsticks for decades, their predictable brightness helping us map the universe. But what if some of those measurements were skewed by supernova that didn't play by the rules? The more we study this cosmic rebel, the more it seems to be rewriting not just stellar physics, but our entire approach to decoding the universe's grandest explosions. When a typical star explodes, it flings out debris at incredible speeds, enough material to forge planets, but usually spread so thin that telescopes can peer straight through it. This supernova did something radically different. Instead of a transparent cloud, it ejected enough matter to build several suns, creating a dense, swirling shroud around itself. That thick veil isn't just hiding the action, it might be the key to understanding why this explosion refuses to end. Picture the aftermath like a cosmic smoke screen, but one that's actively shaping the drama behind it. Normally, supernova debris expands so quickly that it dissipates within months, allowing astronomers a clean view of the fading remnant. Here, the sheer volume of material acts like a celestial blanket, trapping heat and radiation inside. Some scientists speculate this insulation effect could be slowing the explosion's cooling, like wrapping a steaming cup of coffee to keep it hot. The debris isn't just a bystander, it's an active participant, potentially recycling energy back into the system and prolonging the light show. But the real intrigue lies in what that debris contains. Spectroscopic analysis reveals heavy elements like titanium and calcium mixed with vast amounts of hydrogen, an unusual cocktail that suggests the star shed multiple layers at different stages of its death throes. It's as if the star didn't explode once, but unraveled in stages, each eruption adding another shell to the cosmic onion now blocking our view. The proportions of these elements could reveal whether the star was spinning wildly, had a hidden companion, or possessed some other quirk that made its demise so extraordinary. The challenge, that same debris making the supernova scientifically fascinating, also makes it astronomically frustrating to study. Infrared telescopes have had to work overtime to pierce the dusty veil, while radio observations track shockwaves ricocheting through the dense material. Every wavelength of light tells a different part of the story. X-rays reveal the inner chaos, while visible light shows how the outer layers interact with interstellar space. Piecing together these clues is like reconstructing a car crash by studying the skid marks, but on a scale where the skid marks are light years long. What's emerging is a picture far more complex than anyone anticipated. This isn't just a star that exploded, it's a star that engineered its own obstacle course on the way out, leaving behind a puzzle wrapped in an enigma. The more we learn about its debris, the clearer it becomes. This supernova didn't just defy expectations, it rewrote the rules of engagement for stellar death. And somewhere in that swirling cosmic fog, the answers we're searching for are waiting to be found. Humanity's fascination with exploding stars stretches back millennia, long before telescopes or spectrographs existed. Ancient astronomers from China to the Middle East meticulously recorded guest stars, sudden bright lights in the heavens that faded over months. But among these historical accounts, one event stands out as eerily similar to our modern mystery. In the year 1054, Chinese court astronomers documented a celestial visitor so bright it was visible for 23 days in broad daylight, then lingered in the night sky for nearly 2 years. The description matches what we'd expect from a typical supernova, except for one curious detail. Court records mention the star fluctuating in brightness, sometimes reappearing after seeming to vanish, behavior that defies the steady fade of known supernova. Could this ancient light show have been an iPTF14hls-like event? The timing fits. The remnant of SN 1054, the Crab Nebula, lies relatively nearby at 6,500 light-years away, close enough that its light would have been unmistakable to the naked eye. Yet modern studies of the Crab reveal no evidence of multiple eruptions. This leaves astronomers puzzling over whether the ancient observers witnessed optical illusions from atmospheric conditions, or if they truly saw something extraordinary, a supernova that pulsed like ours. Without spectral data or precise brightness measurements, we're left reading between the lines of thousand-year-old star charts. Other historical records deepen the mystery. Korean astronomers in the year 1140 noted a star that remained visible for 9 months, far longer than most supernovae, while indigenous Australian rock art may depict a similar prolonged event near the date of SN 1066. These accounts suggest that what we're seeing today might not be unprecedented, just exceptionally rare. Imagine the frustration of ancient skywatchers, seeing something inexplicable with no tools to study it, just as we struggle now with limited data from 500 million light-years away. The real challenge lies in interpreting these pre-telescopic observations. Before photography or precise magnitude scales, brightness estimates were subjective. Was a star as bright as Venus or merely like Jupiter? Atmospheric dust from volcanic eruptions could make stars appear to flicker, while gaps in records due to cloudy nights might create false impressions of variability. Even the famous supernova observed by Tycho Brahe in 1572, often cited as a benchmark, showed minor brightness fluctuations that modern astronomers still debate. What makes this detective work so compelling is the possibility that answers might lie buried in overlooked manuscripts or forgotten observations. Recently, researchers combing through medieval European monastic records found references to a wavering star in 1284 that doesn't match any known supernova or comet. Could this be another candidate? The search continues, with historians and astrophysicists collaborating to re-examine ancient texts through a modern lens. Every rediscovered record is another piece of the puzzle, helping us determine whether iPTF14hls is truly unique or part of a hidden class of stellar explosions that have been dazzling humanity for centuries. Perhaps the most humbling realization is how much we still rely on those early astronomers. Their meticulous records, etched on bamboo slips or parchment, now serve as crucial data points in our quest to understand the universe's most violent events. The same curiosity that drove them to document strange lights in the sky still drives us today, proof that some questions transcend time, even if the tools we use to answer them have changed beyond recognition. This cosmic enigma isn't just rewriting the rules of stellar death. It's shaking the foundations of astrophysics itself. For decades, supernovae have been the yardsticks by which we measure the universe, their predictable behavior helping us calculate cosmic distances and understand how elements spread through galaxies. But when a supernova like iPTF14hls defies every model in the textbooks, it forces scientists to confront an uncomfortable truth. Our understanding of stellar evolution might be built on incomplete data. Consider how this changes the game. If massive stars can explode in staggered bursts rather than single cataclysms, what does that mean for how we track the chemical enrichment of the universe? Heavy elements like gold and uranium are forged in these explosions, but a prolonged supernova could distribute them differently, perhaps in concentrated shells rather than evenly dispersed clouds. That single tweak might explain why some regions of space are unexpectedly rich in certain metals while others seem barren. The ripple effects extend to black hole formation too. Standard models suggest massive stars either explode completely or collapse directly into black holes with little middle ground. But if stars can partially explode multiple times before their final collapse, we might need to rethink how intermediate mass black holes, those elusive cosmic middleweights, come into existence. Could some of them be the remnants of these drawn-out stellar deaths? Even our cosmic census might need revising. Astronomers use supernovae as standard candles to measure vast distances across the universe, relying on their predictable brightness. But if an entire class of supernova has been masquerading as ordinary explosions while actually burning far longer, how many distance measurements have been subtly off? It's like realizing your ruler was warped after you've already built the house. Perhaps most thrilling is what this means for future discoveries. If one star can upend centuries of astrophysics, what other cosmic phenomena might we be misinterpreting? Could pulsars we thought were solitary actually be hiding companions? Might some gamma-ray bursts be the final acts of these bizarre, multi-stage explosions? Every anomaly like iPTF14hls isn't just a puzzle to solve, it's a key that could unlock doors we didn't even know were closed. The real lesson here isn't that our models are wrong, it's that the universe is far more inventive than we imagined. Just when we think we've mapped the boundaries of stellar behavior, nature throws us a curveball that expands the playing field. And that's the beauty of science at the frontier. Sometimes the most important discoveries aren't the answers we find, but the new questions we never thought to ask. To crack this cosmic case wide open, astronomers need something rare in the fast-paced world of modern science time. Lots of it. Most telescopes are booked years in advance, with researchers competing for precious observing hours. But iPTF14hls isn't just any celestial target, it's a slow-motion revelation that demands patience. Imagine trying to study a forest by only glimpsing individual trees. What we really need is to watch the entire ecosystem evolve, season after season. That's the kind of long-term data that could finally explain why this supernova refuses to fade. Enter the next generation of observatories. The James Webb Space Telescope, with its infrared eyes, is uniquely equipped to peer through the debris shrouding this stellar rebel, analyzing chemical fingerprints invisible to other instruments. It could spot molecules forming in the cooling ejecta or catch hidden energy sources powering the prolonged glow. Even more exciting are ground-based behemoths like the extremely large telescope, currently under construction in Chile. With a mirror nearly 40 meters across, wider than a blue whale is long, it might resolve structures within the expanding debris cloud, revealing whether we're seeing multiple shells from staggered explosions or some entirely new phenomenon. But hardware alone isn't enough. Solving this puzzle requires a shift in how we study transient cosmic events. Traditionally, astronomers focus intensely on a supernova's first few weeks when the action seems most dramatic. iPTF14hls proves we've been missing the full story by packing up our observational tools too soon. Future surveys like the Vera-C, Rubin Observatory's legacy survey of space and time will scan the entire visible sky every few nights, automatically flagging objects that behave unusually. This constant surveillance could catch other supernovae exhibiting similar rebellious traits, helping determine whether iPTF14hls is a lone oddball or the first of a hidden population. The real breakthrough might come from combining multiple wavelengths of light. Radio telescopes could track shock waves plowing through interstellar material, while X-ray observatories monitor the birth throes of a potential neutron star or black hole at the core. Gravitational wave detectors, though not yet sensitive enough for such distant events, might one day feel the ripples from these staggered collapses, offering a completely new way to probe the star's interior dynamics. It's like assembling a jigsaw puzzle where each telescope provides pieces from different parts of the picture. What makes this search so thrilling is the potential for surprise. Every time we've built a more powerful telescope, it's revealed cosmic phenomena we never predicted. Perhaps the key to iPTF14hls lies in some quantum quirk of superdense matter or an exotic particle we've yet to discover. Maybe the star's rotation or magnetic fields played an unexpected role, twisting the explosion's physics into unfamiliar shapes. Whatever the answer, one thing is certain: the universe still holds mysteries that can humble even our most advanced technology. And that's what makes the hunt so irresistible. The clock is ticking, though. As the supernova's glow slowly fades, we're racing to capture every last photon before the curtain falls on this cosmic performance. But even if iPTF14hls vanishes tomorrow, its legacy will endure, pushing astronomers to design instruments flexible enough to catch the next great stellar rebellion whenever and however it decides to reveal itself. There's something uniquely captivating about an astronomical phenomenon that refuses to play by the rules. This unfinished supernova isn't just a curiosity for researchers. It's become a cultural touchstone, sparking discussions in classrooms, art studios, and online forums alike. Part of its allure lies in the sheer audacity of its defiance. We're used to the universe following predictable patterns: planets orbiting, stars burning, galaxies spinning, all moving with clockwork precision. Then along comes this stellar rebel, tearing up the cosmic rulebook and forcing us to confront how much we still don't understand. For scientists, it's more than just a puzzle. It's a humbling reminder that nature always has new tricks up its sleeve. Professional astronomers who have spent decades modeling stellar deaths find themselves poring over fresh data, debating theories in conference halls, and occasionally throwing their hands up in delighted frustration. Graduate students cut their teeth on its light curves, while veteran researchers admit it's the most fascinating anomaly they've seen in their careers. The supernova's stubborn persistence has turned it into a shared challenge across observatories worldwide, bridging disciplines from nuclear physics to computational modeling. But the fascination extends far beyond academic circles. Space enthusiasts have latched onto its story as proof that the cosmos still holds jaw-dropping discoveries within reach of our telescopes. Online, animated visualizations of its erratic brightening go viral, while amateur astronomers share their own observations in forums, contributing valuable data points to the professional community. Artists depict it in swirling nebulae of paint and light, capturing the drama of a star dying on its own terms. There's an almost mythological quality to its resistance, like a cosmic phoenix refusing to be reborn or fade away. Why does this particular event strike such a chord? Perhaps because it embodies the essence of exploration, the thrill of confronting the unknown. In an age where so much information is at our fingertips, genuine mysteries are rare treasures. This supernova isn't just challenging astrophysicists, it's inviting everyone to witness science in real time, complete with false starts, heated debates, and occasional breakthroughs. It transforms abstract concepts like stellar evolution into something visceral and immediate, a celestial drama unfolding before our eyes. The deeper appeal might lie in what it represents. In a universe often portrayed as cold and mechanical, here's proof of its boundless creativity. A star that won't conform reminds us that wonder isn't reserved for fiction. It's woven into the fabric of reality. Whether you're a researcher rethinking decades of theories or a stargazer simply marveling at its story, this supernova does something remarkable. It makes the infinite cosmos feel thrillingly, beautifully unpredictable. The idea that iPTF14hls might represent an entirely new class of supernova isn't just speculation. It's a revolution waiting to happen. For centuries, astronomers have categorized stellar explosions into neat boxes based on their light curves and chemical signatures. But this cosmic maverick fits none of them, behaving more like a shape-shifter than a textbook example. Its erratic brightening, prolonged activity, and unusual elemental fingerprints suggest we're witnessing something fundamentally different, a stellar death that operates by rules we haven't written yet. Consider the implications. If this supernova isn't a fluke but the first of its kind, how many others have we missed? Modern sky surveys detect thousands of supernovae annually, but most get only a cursory glance before astronomers move on. Could there be more rebels hiding in plain sight, dismissed as noisy data or observational glitches? The answer might lie in re-examining old records with fresh eyes. Already, researchers are combing through decades of supernova observations, searching for similar anomalies that might have been overlooked. It's like realizing an animal species you thought was extinct has been living undetected in your backyard all along. The potential ripple effects are staggering. Every new class of supernova reshapes our understanding of stellar life cycles. Take Type 1, a supernova white dwarf explosions used as cosmic yardsticks. Their discovery forced us to rethink how binary stars evolve. Now imagine uncovering explosions where stars die in slow motion or in repeated bursts. Suddenly, models of galaxy formation, element production, even black hole birth rates would need recalibrating. The universe's chemical enrichment might be more complex than we thought, with some stars dribbling out their heavy elements over years rather than scattering them in a single blast. But here's the twist: proving this is a new class requires more than one example. Scientists need to find other supernova mimicking iPTF14hls bizarre behavior, a challenge given its rarity. Current estimates suggest such events might occur once every 10,000 years per galaxy, making them cosmic needles in a haystack. That's where next-generation telescopes come in. Projects like the Vera C. Rubin Observatory will scan the sky with unprecedented depth, potentially catching these oddballs earlier in their outbursts. Even one more confirmed case would transform this from a curiosity into a legitimate category, opening new chapters in astrophysics textbooks. The search for answers doesn't stop at supernova. If stars can explode in ways we never anticipated, what other cosmic phenomena might we be misclassifying? Could some gamma-ray bursts be the final screams of these staggered explosions? Might certain black holes form differently if their progenitor stars died in stages rather than instant collapses? Every anomaly like iPTF14hls isn't just a puzzle, it's a doorway to discoveries we haven't even imagined yet. What makes this possibility so exhilarating is the humility it demands. Just when we think we've mapped the boundaries of stellar behavior, the universe shows us how much territory remains unexplored. Whether iPTF14hls ultimately claims its own classification or forces revisions to existing ones, its greatest legacy may be teaching us to expect the unexpected. After all, if a star can refuse to follow the script after billions of years of predictable burning, what other cosmic surprises are waiting in the dark? Magnetic fields might be the invisible puppeteers behind this cosmic spectacle, twisting the supernova's death throes into something unrecognizable. Stars aren't just balls of gas, they're dynamic, spinning dynamos, and when one as massive as iPTF14hls reaches its end, those magnetic forces don't just vanish. They intensify, wrapping around the collapsing core like cosmic spider silk, channeling energy in ways we're only beginning to understand. Picture a garden hose with your thumb over the nozzle. The water sprays erratically, controlled by unseen pressures. Now imagine that hose is light years wide, and the water is plasma heated to millions of degrees. That's the kind of chaos we're dealing with here. These magnetic fields could explain why the explosion refuses to fade smoothly. Instead of energy radiating outward in all directions, it might be funneled along magnetic highways, creating jets or beams that punch through the star's debris. When those beams point toward Earth, we'd see sudden brightening like a lighthouse sweeping its glare across our telescopes. This could also account for the supernova's stop and go light curve, with magnetic structures inside the collapsing star acting like valves, alternately trapping and releasing energy in bursts. It's a stellar version of a pressure cooker with a faulty release valve, and the results are anything but predictable. But magnetic fields don't just shape the explosion, they might also power it long after the initial blast. Neutron stars, the ultra-dense remnants of many supernovae, are known to have magnetic fields trillions of times stronger than Earth's. If iPTF14hls left behind a magnetar, a neutron star on steroids, its rotating magnetic field could be pumping energy back into the debris, like a cosmic defibrillator shocking the explosion back to life. We've seen magnetars reignite years after their birth, but never in the context of such a prolonged supernova. This could be the missing link explaining why the light refuses to dim. The wildest possibility, magnetic fields might be altering the very physics of the explosion itself. Under these extreme conditions, particles could be accelerated to near light speeds, creating shock waves that behave unlike anything in our models. Some theorists suggest that magnetic turbulence might even slow the collapse of the star's core, stretching what should be a milliseconds-long event into a years-long drama. It's as if the star's own magnetic skeleton is fighting gravity tooth and nail, turning its death into a grueling marathon instead of a sprint. What's fascinating isn't just the scale of these forces, it's how little we truly know about them. Magnetic fields are notoriously hard to study from light years away, and most of our theories come from lab experiments or computer simulations. iPTF14hls offers a rare chance to observe these invisible forces in action, rewriting the rules of how magnetism shapes the universe's most violent events. Every flicker of light, every unexpected flare, might be a message encoded in the language of magnetic fields, and we're just starting to learn how to read it. This supernova isn't just challenging our ideas about stars, it's revealing how much we've underestimated magnetism's role in the cosmos. From galaxy-spanning fields to the quantum forces binding atoms, magnetism is a universal sculptor, and iPTF14hls might be its most audacious masterpiece yet. The question isn't just whether magnetic fields are influencing this explosion, it's whether they've been quietly shaping stellar deaths all along, and we've only now stumbled upon the evidence. If that's true, then the universe's greatest explosions might be far more intricate, far more beautiful than we ever dreamed. This cosmic rebel isn't just breaking rules, It's offering us a masterclass in how the universe's most massive stars live and die. Typically, stars 20 times heavier than our Sun are thought to follow a predictable script: burn bright, collapse fast, explode once. But iPTF14hls reveals a far more dramatic and nuanced reality, showing us that hypermassive stars might perish in ways we never anticipated. Take the way these stellar giants handle their final moments, where an ordinary massive star collapses inward in seconds, triggering a single explosion. Stars like this one seem to fight their own demise tooth and nail. It's as if their immense gravity creates internal battlegrounds, regions where collapse and resistance wage war, resulting in staggered outbursts rather than one clean detonation. This changes everything we thought we knew about stellar death timelines. Instead of minutes-long death throes, we're seeing a years-long struggle, suggesting the final acts of hypermassive stars might be more like epic sagas than sudden finales. The chemical fingerprints left behind tell an equally fascinating story. Normally, supernova debris shows clear layers of elements forged at different stages of the star's life: hydrogen and helium from its outer layers, heavier elements like silicon and iron from its core. But iPTF14hls ejecta are a chaotic mix, with elements that should be separated by thousands of kilometers all jumbled together. This points to violent, repeated mixing during its death throes, like a cosmic blender churning the star's insides with each eruption. Such turbulence could completely alter how heavy elements spread through galaxies, potentially creating strange pockets of mixed chemistry rather than smooth gradients. Then there's the question of what gets left behind. Standard models predict two outcomes for dying stars: either a neutron star or a black hole. But this supernova's prolonged death suggests a third possibility: a delayed collapse where the star lingers in some intermediate state before its final fate. Some theories propose it might form a temporary quasi-star, a bizarre object with a black hole at its core still feeding on the outer layers. Others speculate about exotic neutron stars with unprecedented density, their very existence rewriting our understanding of matter under extreme conditions. Perhaps most intriguing is what this means for the early universe. The first stars were thought to be these hypermassive monsters, blazing brief but brilliant lives. If they died similarly in drawn-out, explosive fits and starts, they would have scattered their elements differently, potentially changing how quickly galaxies could form. It's a cascade effect. One stubborn supernova today might help explain why the cosmos looks the way it does billions of years later. What we're witnessing isn't just a star's death, it's a challenge to our entire cosmic timeline. Every extra day this supernova lingers, every unexpected flare, forces us to reconsider not just how stars die, but how their deaths shape everything that comes after. The universe's largest stars might not go quietly after all, and that changes everything. The bizarre death throes of stars like iPTF14hls don't just rewrite the rules of stellar explosions, they force us to rethink what gets left behind. When a typical massive star dies, the outcome seems straightforward. If the core is between 1.4 and 3 solar masses, it becomes a neutron star. Any larger, and it collapses into a black hole. But this supernova's prolonged, erratic death suggests the process might be far messier, with potential outcomes we've never considered. What if some stars don't make clean transitions into these compact objects at all? Take neutron stars, those ultra-dense city-sized remnants spinning faster than blender blades. Conventional models assume they form in milliseconds during a star's final collapse. But if a star like iPTF14hls dies in staggered explosions, the core might experience multiple near collapses before its final implosion, like a diver bouncing off the board several times before hitting the water. This could create neutron stars with bizarre properties, perhaps slower spins, distorted magnetic fields, or even layered interiors where matter exists in strange transitional states. Some theorists speculate these stutter-born neutron stars might explain mysterious astrophysical phenomena we've detected but never understood, like certain types of erratic pulsars that defy classification. Then there's the black hole question. Normally, we think of their formation as an all-or-nothing event. A star's core crosses a critical threshold and vanishes behind an event horizon in one irreversible plunge. But what if some black holes form gradually, especially in these prolonged supernovae? Imagine a scenario where the core partially collapses multiple times, shedding layers with each eruption before finally succumbing. The result might be a black hole with unusual properties, perhaps surrounded by a turbulent disk of material that took years instead of seconds to fall in, or with a birth ring of debris marking its staggered formation. Even more intriguing is the possibility of intermediate states, objects that aren't quite neutron stars or black holes, but something in between. Quantum physics suggests that at certain densities, matter might exist in exotic phases like quark-gluon plasma or Bose-Einstein condensates. Could iPTF14hls be creating one of these theoretical objects temporarily before its core settles into a final form? The energy required to sustain such a prolonged explosion might be coming from a phase transition we've never observed, a cosmic metamorphosis where the star's heart transforms in stages rather than all at once. This isn't just academic curiosity. The way compact objects form directly impacts how they behave afterward. A black hole born from multiple collapses might have a different spin or gravitational wave signature than one formed instantly. Neutron stars with memory of their turbulent birth could exhibit magnetic field anomalies or emit unusual radiation patterns. If we've been interpreting all compact objects through the lens of single collapse models, we might have missed entire categories of stellar remnants hiding in plain sight. The implications ripple outward to how we study the universe itself. Gravitational wave detectors like LIGO are tuned to recognize signals from clean black hole mergers, but what if some events produce messier, drawn-out signatures from these oddly formed objects? Similarly, pulsar surveys might need to account for neutron stars that don't fit standard evolutionary tracks. Even our cosmic censuses could be off. If some supernova produce compact objects differently, we might have underestimated certain populations. Perhaps most exciting is how this connects to one of astrophysics' biggest mysteries, the mass gap between neutron stars and black holes. Observations show a strange shortage of compact objects between about 2 and 5 solar masses, a range where we'd expect plenty of remnants. But if stars can shed mass unevenly through staggered collapses, some might end up in this gap after all, just with properties that make them harder to detect. iPTF14hls could be the key to solving this decades-old puzzle, revealing a previously hidden pathway for stellar remains. What's truly humbling is realizing how much we've assumed about cosmic endpoints based on incomplete data. For all our advanced telescopes and supercomputers, nature keeps revealing processes more inventive than our theories. Whether this supernova is forging a new type of compact object or simply showing us how diverse their births can be, one thing is certain: the afterlife of stars is far richer and far stranger than we ever imagined. The hunt for cosmic rebels like iPTF14hls has turned into one of astronomy's most thrilling treasure hunts. Armed with new tools and fresh perspectives, researchers are combing through decades of supernova data, searching for any hint of similar anomalies that might have been overlooked. It's like revisiting old crime scenes with better forensic techniques. Suddenly, details once dismissed as noise could be critical clues. The challenge. Most supernova observations are fleeting snapshots captured during brief telescope time allocations. A star that brightens erratically over years might have been logged as multiple separate events or written off as instrument errors. Now, with iPTF14hls rewriting the playbook, every oddball light curve is getting a second look. Recent advances in machine learning are supercharging this search. Astronomers are training algorithms to spot the subtle hallmarks of prolonged supernova, unusual brightness plateaus, unexpected rebrightenings, or chemical signatures that don't match known types. One promising candidate, SN 2020-JKX, showed similar hydrogen-rich spectra and a light curve that refused to fade normally. Though not as extreme as our cosmic rebel, its behavior suggests we might be seeing the first hints of a spectrum between ordinary supernova and true outliers. Another potential match, SN 2018-JKZ, flared repeatedly over 18 months before vanishing, exactly the kind of drawn-out death that would have been dismissed as impossible before iPTF14hls. The real game-changer will be next-generation sky surveys. The Vera-C Rubin Observatory's upcoming 10-year scan of the heavens promises to catch millions of supernova in action, many within hours of their first explosion. This constant surveillance is crucial. Without catching these events early, we might miss their most bizarre phases. Imagine if we'd only spotted iPTF14hls years into its outburst. We'd have never known about its multiple peaks. Future telescopes won't just find more supernova, they'll watch them unfold in unprecedented detail, tracking how their light changes night after night across different wavelengths. Yet, even with perfect data, the search faces cosmic odds. If pulsational pair-instability supernova occur once every 10,000 years per galaxy, spotting another nearby will require extraordinary luck or looking much farther into the universe. That's where another puzzle emerges. As we peer deeper into space, we're also looking further back in time. The first stars in the universe were likely these hypermassive monsters, meaning their strange deaths might have been commonplace in the early cosmos. Some researchers speculate that certain unexplained bright spots in distant galaxies, once assumed to be clusters of ordinary supernova, might actually be individual, marathon explosions from primordial stellar giants. What makes this search so pivotal is what it reveals about scientific discovery itself. For centuries, astronomers categorized supernova based on what their tools could detect: visible light curves and spectral lines. iPTF14hls forces us to wonder how many cosmic phenomena we've misclassified simply because they didn't fit our expectations or observational limits. It's a humbling reminder that the universe doesn't care about our classification schemes. It will always surprise us. Each new telescope we build, each archive we re-examine, might reveal another rule breaker hiding in plain sight. The ultimate prize, finding a whole zoo of these cosmic mavericks, each one challenging our models in different ways. One might show staggered explosions but different chemistry. Another could last even longer than iPTF14hls, fading over decades rather than years. With every new outlier, we'll piece together a more complete picture of how stars truly die, not in textbook simplicity, but in all their chaotic, magnificent diversity. Until then, every flickering dot in the night sky holds potential, reminding us that the universe's greatest discoveries often begin with a simple question: wait, that shouldn't be possible. What are we missing? To crack the code of this cosmic rebel, scientists are turning to some of the most powerful tools in modern astrophysics, not telescopes but supercomputers. Imagine trying to reconstruct a car crash by studying the skid marks, except the vehicles are stars. The crash lasts for years, and the skid marks stretch across light years. That's the challenge researchers face, and it's why advanced simulations have become indispensable. By digitally recreating the extreme conditions inside a hypermassive star's death throes, these virtual laboratories allow astronomers to test theories that would otherwise remain pure speculation. The process starts with staggering amounts of data. Every flicker of light from iPTF14hls, every spectral line revealing its chemical makeup, gets fed into equations that model the physics of stellar collapse. But here's the twist. These aren't just scaled-up versions of ordinary supernova simulations. The star's bizarre behavior forces scientists to include variables they've never needed before, like the possibility of antimatter creation in the core, or magnetic fields strong enough to twist space-time itself. One team at Oak Ridge National Laboratory used a supercomputer to simulate a pulsational pair-instability explosion, tracking how shock waves might ricochet through layers of previously ejected material. The result, a light curve that eerily resembles iPTF14hls stop and go brightening, suggesting the star could indeed be tearing itself apart in stages. Yet simulations reveal just how much we still don't know. When researchers at the University of California tried to model the supernova's energy output, they hit a snag. No standard stellar model could account for its prolonged glow without invoking something exotic, like a hidden magnetar or a black hole siphoning material. This mismatch between simulation and observation is actually progress. It's forcing physicists to consider mechanisms they'd previously dismissed as too improbable. One groundbreaking model even suggests the star's rotation could be key, like a figure skater pulling their arms in during a spin. A rapidly rotating core might collapse unevenly, creating asymmetrical explosions that prolong the spectacle. The real power of these simulations lies in their ability to explore what-if scenarios at cosmic scales. What if the star had a binary companion? What if dark matter interactions were heating its core? Each virtual experiment takes weeks of computation time, but the insights are priceless. Recently, a European team simulated a scenario where the supernova's shockwaves plow into dense, pre-existing gas shells, the stellar equivalent of a firework exploding inside a series of paper bags. The resulting light patterns matched iPTF14hls' erratic behavior surprisingly well, hinting that the star might have been shedding material for centuries before its final outburst. What's emerging from these digital crucibles is a humbling lesson. The universe is far more inventive than our models. Every time a simulation fails to explain the supernova's behavior, it's not a failure, it's a signpost pointing toward physics we haven't yet grasped. And with each iteration, the simulations grow more sophisticated, incorporating quantum effects, general relativity, and even hypothetical particles. It's a race between human ingenuity and cosmic complexity, with the ultimate prize being a whole new understanding of how stars die. The most exciting simulations aren't just replicating what we see, they're predicting what we should look for next. If certain models are correct, iPTF14hls debris field should start showing unusual chemical mixtures in the coming years, or perhaps even faint X-ray pulses from a newborn magnetar. These digital prophecies give astronomers a roadmap, telling them where and when to point their telescopes. In that sense, every line of code is like a message in a bottle, tossed into the ocean of data in hopes that the universe will send back a reply. This marriage of silicon and starlight is more than just technical, it's poetic. We're using machines made of Earth's elements to decode the death cries of a star made of alien ones, bridging the gap between the infinitesimal and the infinite. And somewhere in that digital cosmos, between the ones and zeros, the truth about this cosmic rebel is waiting to be found. The astronomy community is split down the middle when it comes to this cosmic rebel. On one side, traditionalists argue we're witnessing an extraordinary fluke, a perfect storm of stellar conditions that's misleading us into seeing a revolution where none exists. Maybe it's a rare collision of stars or an unusual debris field magnifying the explosion's glow. They point out that extraordinary claims require extraordinary evidence, and until we spot more supernova behaving this way, iPTF14hls could just be nature's way of throwing us a curveball. But the revolutionaries see something far more profound to them. This supernova isn't an outlier, it's a harbinger of discoveries to come, proof that our stellar death models are incomplete. They argue that dismissing it as a fluke ignores the deeper truth. The universe has always been richer and stranger than our theories can capture. After all, history is littered with exceptions that later became categories. Think of pulsars, initially dismissed as possible alien signals until their true nature was understood. The battleground now shifts to new data. Upcoming observations could tip the scales decisively. If telescopes catch similar supernova with staggered explosions, the fluke argument collapses. Conversely, if iPTF14hls remains alone for decades, the traditionalists gain ground. But there's a third possibility, that we've been misinterpreting other supernova all along. Recent re-examinations of past events have revealed subtle oddities once brushed off as noise, brief rebrightenings, unusual chemical signatures. Could these be hints of a hidden population we've overlooked? Technology will ultimately referee this debate. The next generation of gravitational wave detectors might feel the ripples of a pulsational collapse, while 30-meter-class telescopes could resolve debris structures telling us whether the star died in fits or all at once. Until then, the disagreement itself is healthy. It's how science self-corrects. Every rival theory sharpens the questions, pushing observers to collect better data and modelers to refine their simulations. What's fascinating isn't just the divide, it's how civil and collaborative the debate remains. Scientists on both sides share data freely, knowing the stakes are bigger than any single career. Whether this supernova ends up rewriting textbooks or joining the cosmic hall of oddities, the process of grappling with it is expanding our collective imagination. After all, the universe doesn't care about consensus, it just is. And sometimes it takes a stubborn, shining enigma to remind us how much we still have to learn. Gamma-ray bursts have long been the universe's most enigmatic explosions. Brief, blinding flashes of energy so powerful they outshine entire galaxies for seconds. For decades, astronomers have struggled to explain what triggers these cosmic fire craters, with theories ranging from colliding neutron stars to hypermassive stars collapsing directly into black holes. Now, iPTF14hls raises a tantalizing possibility. Could this stubborn supernova represent the missing link between ordinary stellar explosions and those extreme gamma-ray events? The connections might be closer than we think. Consider the timing. Most gamma-ray bursts last mere seconds to minutes, a fleeting burst of energy that vanishes before telescopes can fully analyze it. But a rare subclass called long gamma-ray bursts persist for hours, often accompanied by visible supernova days later. These events are thought to mark the deaths of hypermassive stars similar to iPTF14hls' progenitor, where the core collapses into a black hole while powerful jets punch through the star's outer layers at near light speed. Here's where it gets intriguing. If iPTF14hls represents a star dying in staggered collapses rather than one clean implosion, those delayed collapses could generate repeated energy surges, potentially explaining both the supernova's erratic brightening and why some gamma-ray bursts show unusual afterglows. The energy scales match disturbingly well. While typical supernova release about 10 to the 44 joules of energy, that's a 1 followed by 44 zeros, long gamma-ray bursts can unleash 1,000 times more, precisely the range needed to explain iPTF14hls' prolonged luminosity. Some theorists suggest we might be seeing a gamma-ray burst viewed from an off angle, where the relativistic jets aren't pointed directly at Earth, allowing us to study the surrounding explosion in unprecedented detail. It's like witnessing a fireworks display from the side instead of head-on. You miss the full brunt of the blast but gain a clearer view of the complex structures behind it. Yet there are puzzling mismatches. Gamma-ray bursts usually show telltale signatures, specific patterns in their high-energy emissions, or distinct afterglows in X-ray and radio wavelengths. iPTF14hls lacks these markers, suggesting either that the connection isn't direct or that we're seeing a completely new hybrid phenomenon. One provocative idea proposes that the star's magnetic fields could be redirecting the jet's energy inward rather than letting it escape as gamma rays, creating a sort of frustrated gamma ray burst where the energy leaks out slowly through repeated eruptions. Picture a pressure cooker with a faulty valve. Instead of one clean release, you get intermittent hisses of steam. The implications ripple across astrophysics. If even a fraction of long gamma-ray bursts are preceded by iPTF14hls like supernova, it would revolutionize how we predict and study these extreme events. Current gamma-ray observatories like Swift and Fermi could be reprogrammed to scan areas where unusual supernova erupt, potentially catching the birth cries of black holes in real time. Conversely, next-generation gravitational wave detectors might feel the ripples from these staggered collapses, offering a completely new way to probe the connection. What makes this possibility so electrifying isn't just solving one cosmic mystery, it's the potential to unite two seemingly separate phenomena under a single, breathtaking framework. The universe rarely operates in neat categories, and iPTF14hls might be showing us that the boundary between supernova and gamma-ray bursts isn't a wall, but a vast, unexplored frontier where stars die in ways more spectacular than we ever imagined. Every flicker of light from this cosmic rebel could be writing a new chapter in our understanding of the universe's most violent transformations. Dark matter, the universe's most elusive ingredient, might hold the key to this supernova's stubborn defiance. We've long known this mysterious substance outweighs visible matter 5-to-1, its gravity sculpting galaxies while remaining utterly invisible to our telescopes. But what if its influence isn't just broad and cosmic? What if dark matter particles are tangled up in the violent death throes of stars, subtly altering how they explode? It's a radical idea, but iPTF14hls' bizarre endurance has astronomers questioning whether conventional physics alone can explain its behavior. Picture a star so massive its core becomes a crucible for extreme physics. As it collapses, densities reach levels where dark matter, normally drifting undisturbed through space, might start interacting in unexpected ways. Some theories suggest certain dark matter particles could accumulate in stellar cores over billions of years, acting like invisible weights that slow the collapse. Others propose annihilation events, dark matter particles colliding and releasing bursts of energy that reignite fading explosions. It's like throwing phantom logs on a fire, except the logs are made of particles we've never directly detected, and the fire is a dying star halfway across the universe. The math is tantalizing. Simulations show that if just 1% of a massive star's mass were dark matter, its decay or annihilation could provide enough energy to prolong a supernova's glow for years. This wouldn't just explain iPTF14hls' persistence, it might reveal dark matter's properties. For instance, if the particles are asymmetric, meaning matter and antimatter versions behave differently, their uneven annihilation could create the erratic brightness spikes we've observed. Alternatively, if dark matter interacts weakly with normal matter through some unknown force, those interactions might only become significant during a star's catastrophic collapse, like a silent orchestra suddenly playing at full volume. Critics argue the idea ventures too far into speculation after all. We've yet to definitively detect a single dark matter particle, but proponents counter that extraordinary cosmic phenomena sometimes demand extraordinary explanations. They point to similar puzzles in other fields, galaxies rotating too fast for their visible mass, or the universe's expansion accelerating mysteriously. Each time, the solution required rewriting physics. Why should stellar deaths be any different? The implications stretch far beyond one peculiar supernova. If dark matter actively participates in stellar explosions, it could explain other anomalies like why some supernovas seem under-energetic, or why neutron stars occasionally exhibit unexpected cooling patterns. More profoundly, it might mean dark matter isn't just a passive backdrop to the universe's drama, but an active player in its most spectacular events. Testing this theory won't be easy. Unlike controlled lab experiments, we can't tweak a star's dark matter content and watch the results. Instead, astronomers are hunting for subtle signatures, unusual neutrino emissions during supernova, or gamma-ray patterns that might betray dark matter interactions. Future gravitational wave detectors could also help, as dark matter's presence would alter the collapse's ripples through space-time. What makes this possibility so electrifying isn't just solving a cosmic mystery, it's the chance to kill two birds with one stone. iPTF14hls might be more than a stubborn supernova. It could be a Rosetta Stone for dark matter, translating its invisible influence into observable stellar fireworks. And if that's true, then the universe's greatest explosions might be lighting the way to its deepest secrets. One of the most inspiring aspects of this cosmic mystery isn't just what professional astronomers are discovering, it's how ordinary stargazers have become vital partners in unraveling it. When iPTF14hls first flared to life, telescopes worldwide swung into action, but no observatory can watch the sky continuously. That's where amateur astronomers stepped in, their backyard telescopes and keen eyes filling crucial gaps in the data. Night after night, volunteers tracked the supernova's flickering light, logging brightness changes that might otherwise have gone unnoticed. These observations weren't just supplementary, they became essential puzzle pieces, revealing patterns too subtle for sporadic professional scans to catch. The tools of modern citizen science have transformed what backyard observers can contribute. Platforms like the American Association of Variable Star Observers, AVSO, allow amateurs worldwide to submit precise measurements using nothing more sophisticated than a DSLR camera and a small telescope. For iPTF14hls, this crowdsourced data revealed unexpected mini-flares, brief brightenings that professional surveys missed because they occurred between scheduled observations. One dedicated observer in New Mexico even caught a sudden dip in brightness that later correlated with spectral changes, hinting at fresh debris eclipsing the explosion's core. These aren't just pretty light curves, they're critical diagnostics helping theorists test whether the star ejected material in discrete shells or experienced internal convulsions. What makes this collaboration so powerful is how it democratizes discovery. You don't need a PhD to spot when a supernova brightens unexpectedly, just patience, basic equipment, and a willingness to contribute. Online platforms now pair these observations with professional data in real time, creating a living catalog that researchers mine for clues. When iPTF14hls flared unexpectedly in 2019, it was an amateur in Australia who first alerted the community, triggering urgent follow-ups that captured chemical changes in the ejector. This synergy between professionals and enthusiasts creates a net so fine almost no cosmic event slips through. The impact extends beyond this one supernova. Citizen scientists have identified asteroids, discovered exoplanets, and even spotted rare types of stellar explosions that would have otherwise faded unnoticed. Projects like Zooniverse's Supernova Hunters train volunteers to comb through telescope images, distinguishing real explosions from camera artifacts with an accuracy that rivals algorithms. There's something profoundly human about this collective effort, a reminder that the night sky belongs to everyone, and that cracking its mysteries isn't just for those with access to mountaintop observatories. For aspiring contributors, the barriers to entry have never been lower. Smartphone apps can guide beginners to promising targets, while affordable CCD cameras rival professional gear from a decade ago. Online communities offer mentorship, teaching newcomers how to calibrate measurements or interpret light curves. Some of the most consistent observations of iPTF14hls came from a high school astronomy club in Norway, their data cited in peer-reviewed papers alongside Hubble observations. This isn't just feel-good participation, it's real science, advancing our understanding of the universe one backyard observation at a time. The lesson here transcends astronomy. iPTF14hls reminds us that cosmic breakthroughs often come from unexpected places, not just billion-dollar telescopes, but from the cumulative power of curious minds working together. Every time an amateur astronomer points their lens skyward, they're not just stargazing, they're joining a centuries-old tradition of collective wonder where today's hobbyist might spot tomorrow's revolution. And in that shared pursuit, we're all professionals and amateurs alike, just students of the stars, piecing together the universe's grandest secrets one observation at a time. The pursuit of cosmic mysteries like this unfinished supernova forces us to confront profound ethical questions about how we allocate science's most precious resources: time, funding, and human ingenuity. Every hour spent training telescopes on iPTF14hls is an hour not spent searching for Earth-like exoplanets or tracking near-Earth asteroids. The dilemma isn't just academic, it reflects deeper tensions between curiosity-driven exploration and strategic scientific priorities. Consider the scale of investment required to study such anomalies. Modern observatories like the James Webb Space Telescope operate on tightly scheduled timelines, with thousands of researchers competing for observation slots. Deciding whether to dedicate weeks of Hubble's remaining lifespan to monitor a fading supernova involves weighing potential knowledge gains against missed opportunities elsewhere. Some argue these extreme cosmic events offer unique windows into physics we can't replicate in labs, making them worth prioritized study. Others counter that resources would be better spent on systematic surveys that advance broader understanding rather than focusing on outliers. The debate extends beyond telescope time to fundamental research ethics. Astrophysics operates within finite budgets, often funded by public money. When a single supernova study consumes millions in computational modeling and observation costs, should taxpayers expect practical returns, or is pure knowledge justification enough? Projects like the search for hazardous asteroids have clear societal benefits, while deciphering a distant star's death might seem abstract until you consider how these discoveries underpin technologies like nuclear medicine or materials science through unexpected spin-offs. There's also the question of scientific bias in what we choose to investigate. Flashy anomalies like iPTF14hls attract disproportionate attention compared to equally important but less visually dramatic research, such as mapping dark matter distributions. This cosmic fireworks effect could skew our understanding of the universe toward rare, spectacular events at the expense of comprehending its quieter but more pervasive mysteries. Yet ignoring outliers risks leaving critical gaps after all. Quantum mechanics emerged from studying radiation anomalies that didn't fit classical models. Perhaps the most nuanced consideration is how we define scientific progress. Traditional metrics favor concrete answers, but this supernova's enduring mystery has value precisely because it resists easy explanation. The collaborative debates it sparks between theorists and observers, between traditionalists and innovators, demonstrate science's self-correcting nature. By wrestling with phenomena that defy categorization, researchers hone sharper questions and develop more flexible tools, benefiting all branches of astrophysics. This balancing act isn't unique to astronomy. Medical researchers face similar dilemmas when allocating resources between rare diseases and widespread health crises. What makes astrophysics distinct is the timescales involved. Decisions made today about where to point our telescopes will shape cosmic understanding for generations. The ethical choice may lie not in prioritizing one mystery over another, but in building systems flexible enough to let serendipity guide us while ensuring foundational work continues. After all, today's perplexing outlier could be tomorrow's textbook standard, rewriting not just what we know about stars, but how we explore the unknown. This cosmic rebel does more than challenge astrophysical models. It holds up a mirror to the very nature of scientific discovery. For centuries, we've built frameworks to explain the universe, confident that with enough data and computing power, we could predict its behavior. Then along comes a supernova that laughs in the face of our textbooks, forcing us to confront an uncomfortable truth: the cosmos thrives on exceptions. The real lesson here isn't about stellar physics, it's about the art of staying humble in the face of the unknown. History is littered with moments when nature reminded us of our intellectual limits. In the 19th century, physicists were certain Newton's laws explained everything until Mercury's wobbly orbit revealed the cracks in classical gravity, paving the way for Einstein's relativity. Decades later, astronomers were convinced galaxies were static islands in space, until Edwin Hubble's observations proved the universe was expanding. Each breakthrough followed the same pattern: arrogance, anomaly, and ultimately revolution. iPTF14hls represents the latest chapter in this cycle, a flashing neon sign that reads, "You don't know what you don't know." What makes this supernova's defiance so poignant is how it exposes the gaps in our imagination. We model stars as spheres of gas governed by equations, forgetting that reality is messier, wilder. It's like trying to predict a hurricane's path by studying a glass of swirling water. The ingredients might be similar, but the scales create emergent behaviors no lab can replicate. When simulations fail to explain why this star keeps burning, it's not a failure of science, it's a reminder that the universe will always outpace our models. The true mark of progress isn't pretending we have answers, but having the courage to say we need better questions. This humility extends beyond astronomy. Modern life bombards us with the illusion of certainty: algorithms that predict our preferences, medical tests that estimate lifespans, climate models that forecast decades ahead. We've grown addicted to the idea that knowledge equals control. iPTF14hls drags us back to a more honest relationship with the unknown, where discovery isn't about conquering mysteries but collaborating with them. There's a quiet dignity in admitting that some phenomena can't be rushed into tidy explanations, that some stars demand we sit with their brilliance until understanding dawns at its own pace. Perhaps the most profound impact lies in how it reshapes our cultural narrative of exploration. We idolize eureka moments, but science's greatest advances often come from staring into the abyss of our ignorance. When researchers published their first baffled reports about this supernova, they didn't hide their confusion, they celebrated it. That transparency invites everyone into the scientific process, transforming observers into participants. Few things are more democratic than a universal a shared acknowledgement that wonder isn't the opposite of knowledge but its companion. So as this stubborn star continues its slow fade, its legacy crystallizes. The universe isn't a puzzle to be solved, but a conversation to be joined. Every flicker of light we can't explain, every model that falls short, is an invitation to stay curious, adaptable, and above all, humble. Because the day we stop being surprised by the cosmos is the day we stop truly seeing it. The Vera C. Rubin Observatory isn't just another telescope, it's about to become the ultimate detective for cosmic rebels like our unfinished supernova. Perched high in the Chilean Andes, this groundbreaking facility will embark on a 10-year mission called the Legacy Survey of Space and Time, capturing the entire visible sky every few nights with a 3.2 gigapixel camera. That's like photographing every grain of sand on a beach as the tide rolls in, searching for the one speck that glows unpredictably. For supernova that break the rules, this relentless surveillance could be game-changing. Most telescopes catch stellar explosions by chance or through targeted searches, but Rubin will watch continuously, ensuring no flicker or fade goes unnoticed. What makes this mission so crucial is its ability to spot anomalies early. Imagine if we discovered iPTF14hls weeks into its outburst. We might have missed its initial flares, the very clues that revealed its staggered explosions. Rubin's rapid-fire scanning could catch similar supernova the moment they ignite, letting astronomers track every erratic brightening from day one. Even more exciting, its unprecedented depth might uncover supernova 10 times fainter than current surveys can detect, potentially revealing a hidden population of these cosmic oddballs lurking in distant galaxies. But Rubin isn't working alone. NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will complement these efforts with infrared eyes capable of peering through cosmic dust clouds that veil crucial details. Together, these observatories form a tag team, Rubin spotting the anomalies, Roman dissecting their chemistry and structure. Throw in the James Webb Space Telescope's ability to analyze light from the early universe, and we've got a toolkit that could finally determine whether iPTF14hls is a fluke or the first of a new class. The real revolution lies in how these missions handle data. Rubin will generate about 20 terabytes nightly, enough to fill 20,000 feature-length movies, processed in near real time by machine learning algorithms trained to flag anything unusual. This means not just more supernova, but smarter detection of the ones that defy patterns. Earlier surveys might have dismissed iPTF14hls quirks as noise, but Rubin's AI will prioritize such rule breakers, potentially serving up a buffet of cosmic anomalies for researchers to feast on. Of course, finding more unfinished supernova would raise as many questions as answers. Do they cluster in certain galaxies? Are they tied to regions rich in dark matter or metal-poor stars? Each new discovery would help untangle whether these events stem from stellar physics we've misunderstood or environments we've yet to characterize. Conversely, if Rubin scans millions of galaxies and finds nothing quite like our cosmic rebel that's equally profound, it would make iPTF14hls a once-in-an-era oddity, a stellar unicorn whose very rarity demands re-evaluating how stars can die. Beyond detection, upcoming gravitational wave observatories like LISA could add a completely new dimension. While current detectors like LIGO sense the final milliseconds of black hole collisions, LISA space-based precision might catch the weeks-long ripples from a pulsational supernova's staggered collapses. Imagine pairing Rubin's optical alerts with LISA gravitational wave fingerprints, a multi-messenger approach that could finally crack the code of how these stars implode. The stakes couldn't be higher. If Rubin finds even one more supernova mimicking iPTF14hls Defies, it would prove our models of stellar death are incomplete, opening new chapters in astrophysics. If it doesn't, we'll face an even thornier puzzle: why this star in this galaxy at this time decided to rewrite the rules alone. Either way, the universe is poised to deliver its verdict, and thanks to these next-generation missions, we'll be watching. Studying a cosmic rebel like this unfinished supernova isn't just a scientific challenge, it's a logistical and financial marathon. The tools needed to decode its secrets don't come cheap. Hubble telescope time costs roughly $30,000 per hour, while supercomputer simulations demand millions in processing power. Add the price tags of next-generation observatories like the James Webb Space Telescope or the Vera-C Rubin Observatory, and the bill for unraveling this mystery could fund entire space missions. So how do we justify pouring such vast resources into studying a single, stubborn star halfway across the universe? The answer lies in understanding how fundamental discoveries ripple through society, often in ways no one could predict. Take the Hubble Space Telescope as an example. When it launched in 1990, critics questioned its multi-billion-dollar price tag. Yet the technologies developed to fix its flawed mirror revolutionized LASIK eye surgery, while its imaging sensors became the blueprint for modern digital cameras. Similarly, the algorithms created to process iPTF14hls erratic light curves are now being adapted to detect subtle patterns in medical scans, potentially catching diseases earlier than ever before. The pursuit of cosmic knowledge has a knack for spinning off innovations that touch everyday lives, even when the stars themselves remain distant abstractions. Then there's the economic engine these projects sustain. Building cutting-edge telescopes employs thousands of engineers designing precision optics, software developers writing code to handle torrents of data, technicians maintaining observatories on remote mountaintops. The Vera-C Rubin Observatory alone supports over 500 jobs across 14 countries, fostering expertise that spills over into industries from aerospace to artificial intelligence. These aren't just expenses, they're investments in human capital, seeding skills that drive technological progress far beyond astronomy. Yet the toughest challenge isn't funding, it's patience. Science moves at the speed of curiosity, not quarterly reports. iPTF14hls has been defying expectations for nearly a decade, and it might take another 10 years before we fully grasp its secrets. In a world obsessed with instant results, justifying long-term investment in open-ended questions requires reframing how we measure success. The payoff might not be a eureka moment, but a slow accumulation of insights that quietly reshape our understanding of physics, chemistry, and even the origins of life itself. Critics argue these funds could address pressing earthly problems: climate change, poverty, disease, but this overlooks how interconnected knowledge truly is. The same quantum mechanics explaining stellar explosions also gave us MRI machines. The same atmospheric models mapping distant exoplanets now sharpen our climate predictions. By probing the universe's extremes, we develop tools and perspectives that eventually circle back to Earth, often solving problems we didn't yet know we had. The ultimate justification may be more philosophical than practical. Humans have always looked to the stars not just for answers, but for better questions. Every dollar spent unraveling this supernova's mystery is a bet on our collective imagination, a wager that by stretching the boundaries of what we know, we'll discover not just how stars die, but how much more we're capable of understanding. And in a universe that constantly surprises us, that might be the most valuable return on investment of all. Astronomy has always been a global endeavor, but this unfinished supernova has turned international collaboration into something extraordinary, not just a convenience but a necessity. When iPTF14hls first defied expectations, the alerts went out worldwide within hours, triggering a coordinated response that spanned continents. Telescopes in Chile tracked its brightness fluctuations while spectrographs in Hawaii dissected its chemical composition. European researchers shared computational models with teams in Japan, and Australian radio telescopes monitored shock waves racing through the debris. This wasn't just scientists working in parallel, it was a real-time, around-the-clock conversation, with each discovery building on the last, regardless of borders or time zones. What makes this collaboration so remarkable is how it transcends traditional rivalries. In a field where groundbreaking discoveries often lead to fierce competition for credit, iPTF14hls has become a rare unifying force. Major observatories, usually booked years in advance, began offering discretionary time to monitor the supernova, prioritizing collective understanding over individual projects. The Atacama Large Millimeter Array in Chile, typically focused on galaxy formation, pivoted to study the supernova's dust clouds. Meanwhile, NASA, a swift satellite designed to catch gamma-ray bursts, adjusted its schedule to capture X-ray emissions that might reveal hidden energy sources. This level of flexibility is almost unheard of in modern astronomy, where instrument time is meticulously allocated. The data sharing has been equally unprecedented. Normally, astronomers guard observations closely until publication, but teams studying this cosmic rebel began uploading findings to open servers within days. A researcher in India might spot an unusual spectral line and share it with a theorist in California, who'd test it against simulations and loop in radio astronomers in South Africa to check for corroborating signals. This rapid-fire exchange has accelerated the pace of discovery, turning what could have been years of isolated analysis into months of collective breakthroughs. Language barriers and cultural differences fade when faced with a mystery this profound. Weekly video conferences connect scientists from over 30 countries, with discussions seamlessly switching between English, Spanish, and Mandarin as colleagues help each other articulate complex ideas. Early career researchers in Brazil find themselves debating with Nobel laureates in Germany, their contributions valued not for institutional prestige but for fresh perspectives. One graduate student in Poland noticed a subtle pattern in the light curve that veteran observers had missed, a discovery that reshaped how theorists modeled the star's internal shocks. The tools enabling this teamwork are just as innovative as the science itself. Cloud-based platforms allow astronomers to annotate the same dataset simultaneously, while machine learning algorithms sift through mountains of observations to flag anomalies for human review. Citizen scientists, many with no formal training, contribute vital observations through platforms like Zooniverse, their collective eyes spotting details automated systems might overlook. This isn't just collaboration, it's a new model for how science can operate in the digital age, where expertise flows as freely as the data it interprets. Perhaps the most unexpected outcome has been how this supernova is training the next generation of astronomers. Doctoral students who have never met in person co-author papers with peers on opposite sides of the globe, learning to navigate cultural nuances alongside cosmic ones. Summer schools dedicated to iPTF14hls analysis have sprung up from Sweden to South Korea, blending lectures on stellar physics with workshops on intercultural communication. The result is a cohort of young scientists who see collaboration not as an obligation, but as the essence of discovery. This spirit extends beyond academia. Amateur astronomers worldwide, from backyard observers in Canada to high school clubs in Kenya, have become vital partners, their telescopes filling gaps in professional coverage. When monsoons obscured views from India or winter storms closed mountaintop observatories in Arizona, volunteers in drier climates picked up the slack. Their contributions aren't just supplemental. They've captured sudden flares and dimming events that would otherwise have gone unrecorded, proving that cracking cosmic mysteries isn't reserved for those with advanced degrees or million-dollar grants. The supernova's greatest gift might be the blueprint it's creating for future collaborations. The protocols developed to share data, the networks forged across disciplines, the trust built through open dialogue. These are templates for tackling other grand challenges, from climate change to pandemic response. iPTF14hls has shown that when humanity pools its curiosity and ingenuity, even the universe's most stubborn secrets start to unravel. And in a world often divided by borders and ideologies, that's a lesson shining far brighter than any exploding star. The unfinished supernova iPTF14hls stands as a cosmic paradox, a brilliant enigma that refuses to surrender its secrets. Years after its discovery, it continues to flicker and fade on its own defiant timeline, challenging astronomers to rethink everything from stellar life cycles to the fundamental laws governing explosions in the void. What makes this mystery so captivating isn't just the scientific upheaval it's caused, but the way it embodies the very spirit of exploration. Somewhere in its erratic pulses and stubborn glow lies a truth we haven't yet imagined, a reminder that the universe's greatest discoveries often begin with the humbling admission, we don't know. Consider how far we've come since that first baffling observation. What began as a single anomaly in the data has blossomed into a revolution in astrophysics, spawning new theories about pulsational collapses, magnetic feedback loops, even dark matter's potential role in stellar death. Each hypothesis is a testament to human ingenuity, our relentless drive to make sense of the incomprehensible. Yet for every question answered, iPTF14hls poses a dozen more, like a cosmic matryoshka doll with endless layers waiting to be unpacked. The beauty of this mystery lies in its unresolved nature. Unlike textbook cases that fit neatly into predefined boxes, this supernova thrives in the liminal space between understanding and wonder. It's a celestial conversation starter, bridging the gap between professional astronomers debating in conference halls and amateur stargazers peering through backyard telescopes. Whether it's a rare pulsational pair-instability event, a magnetar in disguise, or something entirely new, the speculation itself is a celebration of curiosity, a collective exercise in stretching the boundaries of what we believe is possible. What's next in this cosmic detective story? The answer may depend as much on technology as on theory. Upcoming observatories like the Vera C, Rubin Observatory and next-generation gravitational wave detectors promise to scan the skies with unprecedented precision, potentially catching similar supernova in their earliest stages. Meanwhile, advanced simulations will continue to test wild new ideas, from quantum effects in collapsing cores to exotic particle interactions. But here's the twist: even if we never fully crack iPTF14hls code, the pursuit has already reshaped astronomy, proving that the most valuable discoveries aren't always answers. Sometimes they're better questions. So as we watch this cosmic rebel's light slowly fade, let's not see it as an unsolved puzzle, but as an invitation. An invitation to stay humble in the face of the unknown, to embrace the thrill of not knowing, and to keep looking up with the same wide-eyed wonder as those ancient astronomers who first recorded guest stars in the night sky. After all, the universe doesn't owe us explanations, it offers mysteries. And in that endless dance between question and discovery, between confusion and revelation, lies the true magic of exploration. Whether iPTF14hls ultimately surrenders its secrets or remains an eternal riddle, one thing's certain: the stars will keep exploding, the cosmos will keep surprising us, and the next great mystery is already out there, waiting to ignite our curiosity all